Very good evening and wishing everybody a very happy new year. Today we are thrilled to welcome Dr. Swagat Saurav Mishra, a theoretical cosmologist whose work explores one of the most profound mysteries of our universe, why cosmic expansion is accelerating. Well, currently, Dr. Swagat is a senior researcher at the Institute for Basic Science in South Korea, where he is currently, you can watch him live. Dr. Mishra works at the frontier of modern cosmology, studying dark matter, cosmic inflation, and the physics of the early universe. His research connects deep theoretical ideas with cutting edge observations, helping us understand the repulsive forces shaping cosmic expansion. Beyond academia, he is also a passionate science communicator, featured on platforms like Numberphile and 60 Symbols, where he brings complex ideas to a global audience. Today, he joins us to unpack the fascinating concept of cosmic repulsion, what it is, why it matters, and what it may reveal about the ultimate fate of the universe. Dr. Swagat is an extremely busy person. I'm extremely thankful and honored to get him live on my channel, Physics for Students. Sir, Happy New Year and a warm welcome.
Hi, Shaunak. It's a pleasure to be here. Happy New Year to you and everyone who is listening to this. I think this is a great channel, and I looked at many of your podcasts and very wonderful topics of discussion, and so I'm very happy to support in any way.
Thank you, sir. So we already got a hello, sir, good evening from somebody called Sosafi4072. So just a way we would proceed the broadcast, rules come first. So what we are going to do is that sir has designed an extensively deep and a fascinating presentation. And it is in a PDF file, which I'm going to share right now. And what Dr. Swagat is going to do is that we will carry on with the usual flow of the program, because it is something serious and something very extensive. And in between, I would request all the subscribers and viewers, you are all welcome to ask questions. If the questions are something that will be answered by Dr. Swagat in due course of time, I would request everybody to be patiently waiting so that these questions are answered. Otherwise, you are all free to ask any question, and we will pause, and sir will be answering this question. So, sir, I will just, with your permission, share the screen, and we will start with the program today.
For sure.
Is this fine with the screen, or shall I go to the next part?
Absolutely, we could go to the next slide, which is basically telling you a little bit about what is modern cosmology. I'm sure many of you are familiar with cosmology, but just to get the ball rolling, cosmology is the study of nature across many length scales. From the very microscopic length scales, which was more important in the very early universe, all the way to the extremely largest scales in the universe that we see, which is the size of the observable universe. So it spans a large range of length scales and energy scales, and it involves physics across different sort of disciplines. For example, particle physics, gravitation, astrophysics, quantum field theory, thermodynamics, statistics, engineering, and all of that. And then there are many types of experiments which are important for cosmology, like the Large Hadron Collider for particle physics, and then cosmic microwave background, and the way galaxies cluster, then Big Bang nucleosynthesis, and supernova, a particular type 1 is supernova, etc. So it's a very vast topic. Although today we will focus on only a few things to discuss. Yeah, this is again a slide. If you're a student, you're probably familiar with this. I'm just saying that our nature seems to have 4 fundamental interactions: the electromagnetic force, strong force, weak force, and gravity. And at very low energy scales, they all look very different. But it's possible that at very high energy scale, all of these interactions could be just a part of one framework. But they're all important.
Yeah, sir, just one quick question. This strong force is being totally explained by quantum chromodynamics.
Yes. Yes.
Okay.
So the strong nuclear force at very high energies is explained by quantum chromodynamics, which is a well-studied quantum field theory.
Okay.
Yes. And but in cosmology, we are discussing the big universe, and there are some facts about our universe which are very interesting and important. For example, our universe is big. Like I just said, it's at least 10 to the power 24 kilometers big, and we don't know how big it actually is. And it is old. It has been there at least for 13.8 billion years. It is clumpy, so it has a lot of structure, like galaxies and all are clustered together. So it's very clumpy today, and it's evolving. It's not a constant state. It's constantly evolving as time progresses, and it's been expanding since 13.8 billion years. And the way we sort of parameterize or understand the expansion of the universe is through this Hubble parameter, which says that if we go to two far away distant places in the universe, these two distant places are changing as a function of time, and at what rate the distance between 2 points are changing is this Hubble. So if you wish, we can understand expansion in more detail, but they would come in some subsequent slides. But there are another two interesting things which I would like to mention briefly, is that
Shall it should
in the
stay at
previous
the same
slide,
slide? Okay, okay.
yeah,
Yeah.
yes, please. That universe, we also understand that universe has structure today. We also understand how this structure has grown over a function of time. Like from the past, when universe was very, very homogeneous with very tiny inhomogeneities here and there, to today, where we have a clustered galaxy clumpy structure called cosmic wave. So that is something that we have understood in the last 3 decades, and it's a great success of cosmology as a field. And coming back to today's topic, in this journey of understanding the universe, we have figured out that our universe appears to be accelerating twice. So it's not only expanding as a function of time, the expansion rate seems to be accelerating. There is an early period of acceleration in the very, very early universe, where within a second, universe expanded by a huge amount in an accelerated way. And then more close to today, universe has also started accelerating. So it was expanding in an accelerated way, then it started expanding slowly for a long time, then again it's beginning to accelerate. So we are going to focus on these accelerated epochs of expansion in the universe today. By the way, as I speak, please ask me questions in between any slides that you have without waiting for it, since this is not a talk, it's more like a conversation and trying to answer your questions.
Anyone, please feel free to ask question to sir, because I know his huge encyclopedic knowledge in terms of from the very small to the very big. So let us take, take this opportunity to learn a lot from him. Yes, sir. Please continue.
And I should also say that all the slides that I have are too much, and I'm not going to go through all the points that I have noted. I'm just going to say some basics initially so that it gets you thinking and questions come, and then we can sort of address them. Okay. So there's this standard paradigm of cosmology. This is sometimes known as hot Big Bang theory. It just says that when you go back early in the universe, in this diagram, if you go to the region where it's red color roughly. So this diagram is scale factor, or basically size of the universe growing as a function of time. And on the y-axis, I'm plotting density of different substances. What happens to different substances as the size of the universe grows? The early universe was radiation dominated. So it had mostly radiation-like particles traveling almost at the speed of light. They are dominating the density of the universe. But their density falls pretty fast in an expanding universe. First of all, as universe expands, the same number of particles are in a bigger volume, so their density goes down. Plus, if you're radiation, individual energy of radiation also gets diluted as a result of expansion of the universe. And so the radiation actually falls much faster. But there are also like heavy things like nucleus and atoms and etc., which are like matter. We call them matter, and matter sort of falls slightly slow compared to radiation. So eventually, you see this green color part where matter starts to dominate, and universe becomes matter dominated. Um, that happened around a time when universe was roughly 3,000 times smaller than today's size. And then that continued for many years, many billion years. And today, it seems there is a dark energy, which is what we will talk more today.
Sir, sorry to interfere.
Yes,
We got two questions. I'm just
please.
pausing the screen sharing so that we can take the questions, and then again I will come back. Now, the first question seems to be a little bit, sorry, not well framed, but the essence is that if the rate chain of expansion is increased, how we are able to point it with time from early universe?
Very nice question. So let me try to answer this recent phase of accelerating expansion, which we usually call the dark energy dominated accelerating expansion. This one is so universe started accelerating recently when its size was roughly half of its present day size, and this was about 5 to 6 billion years ago. Okay, and how do I know? Here is how you can know. Suppose you have a star which undergoes supernova, but these are particular types of stars, so that when they undergo supernova, you know what is their actual brightness of the system. How much energy are they pumping into space per unit time? So you know them. These are called standard candles. And then if between them and today, universe is accelerating, then this light has to travel longer distance to reach us. So they will look dimmer than they would if we were not accelerating but only moving slowly away. So by looking at how dim distant supernova looks like, you can actually say whether universe is accelerating in between. So that's one way to know whether universe is accelerating. And in fact, that's how we actually discovered in 1998 that universe is accelerating at present.
So the next question I have got, sir, what are your views on conformal cycling cosmology model of Sir Roger Penrose?
This is first of all, you're welcome to ask such questions. This is a good question. And this is a question that we may answer towards the end when we go
Right,
from our standard paradigm of cosmology to something which is non-standard. Is that okay
right,
if we do
right.
that?
Yeah, absolutely. So physics C1D, you need to wait because sir is trying to explain in a very methodical way. So I will go back to the screen sharing and we can proceed, sir. I'm removing myself. Whenever it is required, I will come in the screen. All yours.
Great. So now the universe has become dark energy dominated and it's accelerating. And there's this puzzle that what is dark energy and how can universe accelerate really, right? We can understand that. And let me see if I have some slides to explain how universe can accelerate. Maybe we have to go a few slides ahead. So if we go a few slides ahead, maybe two more, three more. Okay, let's do the following. Before we answer how universe can accelerate, let's go to a slide, a slide before this slide. I want to update you first. What do we know today? What is the most advanced or most updated?
This one is okay, sir. Is this one we stick to this, right? Okay, thank you.
The most updated mm, knowledge of our universe. So this is what we'll call a modern or extended Big Bang theory. Not the old hot Big Bang theory, but it's an extended hot Big Bang theory, which is very similar to the old Big Bang theory, which I showed you in the previous diagram. You have this red color part, which is radiation domination. You have this slightly bluish green color part, which is matter domination towards its right. And finally, a dark energy dominated accelerated expansion. However, we have strong evidence to believe that at very early times, there was a phase in which universe was expanding in an accelerated way, which is cosmic inflation. And I'm going to talk about inflation for the next 10, 15 minutes, not in a flow, but for the next 15 minutes of the podcast with your questions. So we will learn a lot more about cosmic inflation. But there was strong hints. We have strong hints that there was a period of cosmic inflation in the very early universe. And somehow, universe made a transition from this inflationary phase to the hot Big Bang radiation-dominated phase, and then it evolved all the way to today. So that's the modern view of the universe. To show you this in a table, if we go to the next slide, this kind of updates you about different timeline of different events. So in a if universe is expanding and if you go back in time, then faraway galaxies which are going away from each other will be closer and closer and closer, and you will eventually reach a point where the density and temperature of the universe is so high that you cannot have atoms. Everything is in a plasma phase. This is this hot Big Bang phase. But if you keep going back and back, extrapolate it further and further and further into the past, you will reach a point in a finite time in past where the scale factor, the size of the universe becomes zero and temperature becomes infinite. This is usually called the Big Bang singularity. We really don't know whether we can push our current theories so far back in time. So Big Bang singularity is kind of a too much extrapolation of known laws of physics. Also, when things become very dense, if the energy scale becomes higher than Planck scale, then Einstein's theory of gravity is not a good description. So we also need to update our theory of gravity, and quantum effects become important, etc. That's why I put a question mark in front of Big Bang singularity. So that's an important thing, that the singularity is not actually part of cosmology necessarily. When we say Big Bang theory, it doesn't have a Big Bang singularity necessarily. It just says that there was a hot and dense at early times and clumpy today. Okay, great. And then at some point, there was an inflationary phase when universe expanded very, very fast in an accelerated way, which I'll talk in more detail. That happened for a fraction of a second. And then the hot Big Bang started. We also don't understand how you go from inflation to hot Big Bang, which has a lot of particles and radiation. So that's, again, an open problem, which we can talk today also if you're interested. And then slowly, when about 1 second after this classical singularity, which may not even be there, this is just a time-keeping device. Okay, so after 1 second of that classical singularity, temperature of the universe dropped below 10 to the power 10 Kelvin. So the first nuclei, etc., started to form. And the first helium nuclei were sort of cooked in that temperature. So that's an important event. And about 60,000 years ago, universe became from radiation to matter dominated. And the first atoms, the hydrogen and electrons, hydrogen nucleus and electrons started combining and form hydrogen atoms, for example, around 380,000 years ago, after the classical Big Bang. And then for star formation, etc., happened after 1 million years or so. And today we are doing this podcast after about 13.8 billion years, when the temperature of the universe is very low. It's 2.73 Kelvin, which is minus 270 degrees below 0 degrees Celsius. So it's a long journey, basically.
Sir, we have got two quick questions coming up. I'm just stopping the screen share. We'll come back to that. Yeah. So the first question is that from Nitish Kumar Meher. He's telling, you said the distance between 2 points changes due to the expansion of universe. So does it mean the motion of galaxies are due to both the expansion of universe and also their inherent motion?
An absolutely great question. The way we study it in two steps. In step one, if you go to very large distances, everything is very, very homogeneous and isotropic, very, very smooth and uniform. So even though there are lots of galaxies there, it's very smooth. So most of the expansion really comes from the expansion of the universe. So faraway galaxies are moving really because universe is expanding. But if you can trace out local motion of galaxies, go to a cluster of galaxies and see what they are doing. They're also moving around their center of mass there. And they may be going away from each other as a cluster, but individually they're moving. So inside that cluster, maybe one galaxy may be falling towards their center of mass, and the other may be falling on the other way towards the center of mass. So they would have different velocity with respect to us. There's a term that we use in cosmology. It's called peculiar velocities, and they're very important part of cosmology. But so far, I have been only talking about the overall cosmic motion or basically expansion of space. But good question.
Okay, so Nitish Kumar, you got your question answer. Okay, Raghav Manchanda, a very old subscriber and a fellow associate. Now he is asking this, sir, please explain Narlikar steady state theory, which is challenging the Big Bang theory.
Again, very good question. We could go back to this question at the end of the podcast, but I would like to say something about the steady state theory, which was a great idea in the 50s and 60s, was originally by Fred Hoyle and Bondi and Gould. This idea basically says that universe is expanding, but the state of the universe is not changing. There are always galaxies and there will always be galaxies. There was never a hot Big Bang phase with a plasma. And so as universe expands, there is constant matter creation, and that sort of forms galaxies. So if you look at the early universe, it will look exactly same as today's universe. That, I think, observationally, it was ruled out in 1965 when the first thermal radiation from the hot Big Bang phase was detected. So it was a great theory, and I think observationally it is not correct, but it has some elements in it which could be used for modern theories, etc., etc. The overall picture is not correct, but the physics was great.
Okay, so Nitish is telling thank you, sir. Raghav is telling thank you, sir. We go back to our slide. Yeah.
Right. Right, so this is an updating you what was going on in the universe. Since we're talking about cosmic microwave background radiation, this ancient light from the hot Big Bang phase, maybe let's just spend a minute on it. It was discovered in 1965 by Penzias and Wilson. It's a very, very almost perfect black body radiation, which gives you a sort of proof that universe was in a hot and dense thermal state at very early times. Today, if you measure the temperature of this cosmic microwave background across the sky, this light is coming to you from all directions because the whole universe was in a plasma state. The emitted light in the early universe was several thousand degrees. So it was a greenish yellow color light, basically visible light. But over the billions of years, this light has been stretched or redshifted, and today it's in microwave. So that's why it's called cosmic microwave background radiation. And the temperature today is not thousands of degrees, but 2.73 Kelvin. So it's a very cold, but it's ever-present radiation, and it dominates the microwave sky all across in the universe. So it's an important thing. And if you measure its temperature, it's almost same. But if you have a better thermometer, which can measure temperature up to 4 or 5 decimal places, then you would see that in some direction in the sky, you have slightly higher temperature. In some direction, you have slightly lower temperature, which is this diagram in the below. And so universe was very smooth up to 3 or 4 decimal places, but the temperature and density were slightly different in the plasma. And that is very crucial for the existence of all of us today, because this small fluctuation started growing over billions of years, and they formed the galaxies, which is the origin of all structure.
So shall I go to the next slide?
Yes, Shaunak, let's go to, this is basically all I'm showing is you send a satellite to space and it studies the microwave sky and it can give you a map of temperature. And in this slide, if you look at the map, so the map has the quality of thermal camera, which can measure temperature. It has improved a lot since 1990s to this decade, and we have measured these fluctuations being present at all length scales, or basically all angular scales. If you look at the sky on large angular scale, you'll see some temperature difference. If you look at periodically smaller angular scale, you'll see similar temperature difference, and you can have a full map of temperature difference as a function of angle. But when you stare at this amazing image here, you can ask yourself 2 questions. First of all, there's this hot and dense plasma in the universe, right? You can ask, where did this plasma come from? Why the universe had a hot and dense plasma at early times? The second question you can ask is, what created this pattern of fluctuations? And that is a crucial thing for today's discussion.
Okay, next slide, I will go. Yeah, this part.
Great. So now we are coming to things that are very important for today's podcast. First thing, if you look at this map carefully, you see that I've made these circles in red color. That is the maximum distance that light could have traveled from the beginning of the universe all the way until this time when this light was emitted. Okay, so that's the maximum length over which communication could have happened in the early universe. Yet, and that's just a little, it's about 1 degree in the sky, 1 angular degree. Yet the whole sky has the same temperature in CMB, 2.7255 Kelvin. How is it possible that there are these completely uncorrelated regions which never talk to each other, yet all of them have the same temperature? So one way is to some magic happen, which kind of created all of this non-talking region to have same density and temperature. That's possible. This magic, you can put it on quantum gravity or something. Or you can come up with a better theory which actually explains why these distant parts of the universe have the same properties. Okay, we will see that. But if we go to the next slide, this slide just says that if you go to a hot spot and a cold spot on this map, the temperature difference between them is only 0.00001 Kelvin. Okay, so this is actually very smooth. Okay, so great. Now we'll skip a lot of slides because I had some diagrams which I can come back and explain to other people. Yeah, first of all, I'll stop here and check if somebody has a question about whatever I have said so far.
Yeah. So anybody have any question till now, please ask us, because we are now moving to another part of the structure of the universe. So I think, sir, no, we don't have any questions. So is this a slide you want me, or shall I
Sure.
go earlier to this? Okay.
Yeah, this is an important slide.
Yeah.
All it says is if you map these fluctuations carefully, these fluctuations have very, very special properties. First of all, you would see at different length scales, the fluctuations have exactly same amplitude. Okay, that means that the primordial fluctuation, whatever created these spots in the temperature, the parent fluctuation or the primordial fluctuation, it had a property called scale invariant, which means on smaller length scales, fluctuations have similar amplitude as on larger length scales. And this is a very important hint. So it's almost fractal-like fluctuations present in the early universe. And it also turns out that fluctuations in matter, like electrons, nuclei, whatever was present, dark matter, and fluctuations in photons, fluctuations in neutrinos, all of them were created by the same mechanism, one parent field. That's another important hint, which has in our cosmology jargon, we call it adiabatic fluctuations, but it simply means one parent field. And there's a third important hint, is that these are fluctuations. So there's a probability of having high temperature and low temperature. And we can talk about average quantities, etc. The distribution function seems to be a Gaussian or a bell curve distribution, which means probability of having zero fluctuation is maximum. That's why universe is smooth, almost homogeneous and isotropic. Probability of having slightly smaller fluctuation is slightly high. And then as you go to very large fluctuations, it has almost no probability, zero probability. So this is a very, very Gaussian fitting curve. And these three together provide a strong hint, if we go to the next slide, about the origin of these fluctuations. What created these fluctuations? It turns out a specific phase in the very early universe could have created these exact types of fluctuations. And that phase is this cosmic inflation that I have been telling you about. So cosmic inflation actually answers many things about many properties about the universe. First thing, it says why distant parts of the universe have same temperature, etc., which I'll say in a while. It also explains this exact pattern of fluctuations, which I'll show you in the next few slides. So let me tell you what is cosmic inflation. In Einstein's theory of gravity, which is general relativity, which Sean's favorite topic, which he talks about a lot in this channel. So in general relativity, gravity is caused not just by mass, unlike in Newton's theory, but it's caused by mass and energy and pressure and elasticity and shear and all of that. Okay, they all contribute to gravity. In a completely homogeneous and isotropic distribution of matter, which is true for our universe, roughly, what would happen to the expansion of space really depends on the combination of density of the substance that you have and pressure of the substance you have. In particular, density plus 3 times pressure. That decides whether expansion of space would slow down or accelerate. You can get acceleration if density plus 3 times pressure is negative, which means pressure is less than minus 1/3 of density. Usually you don't expect this, right? See, if you think purely by intuition, if you have universe is filled with dark matter and galaxies and all, as universe expands, these things are pulling each other. So universe will slow down and slow down and slow down. Just like when you toss a coin, it goes up and slows down. If you toss it with a speed greater than escape velocity, then it will keep slowing down, but it will go away, never stop and come back. If you toss it with a velocity smaller than escape velocity, it will go for a while, it will stop and come back. But those are the two things that you will expect from intuition. What is happening to our universe is you toss it, it slows down for a while, then speeds up. And that's the mystery. And it turns out if you fill the universe with a negative pressure substance, then you can get acceleration. But this inflation that I'm saying, it happened in the early universe. It did not last forever. It lasted just for a second. So whatever this negative pressure substance is, it came to existence for a fraction of a second. So it's radioactive. And then it decayed away. So when it existed, it made the universe accelerate at a very rapid rate. And then when it went away, decay away, it dumped all of its energy into photons and dark matter and electrons and all particles that we see. And that created the hot Big Bang phase. So that's the basically outline of the story. Yes.
Sir,
Do we have questions?
we have got a question. Just a second. Yeah, so Nitish is asking, how do we know that this CMB, cosmic background, microwave background radiation, is due to the Big Bang and not due to any other event?
Yeah, first of all, there's something that I made clear, but I want to make it clear again. When we say Big Bang in the Big Bang theory, it is not about any particular bang or singularity. It is a state in which universe was in a hot and dense plasma state. Okay? So when we say Big Bang theory, we do not mean there was any bang. Okay? Of course, we can think of, was there a bang and why did universe start expanding? This is an important question. But when we say standard Big Bang theory, all we mean is there was a time when universe was in a hot and dense plasma phase. So
right. So
the
mean,
question is,
we should not imagine anything like a firecracker or something. It bursted. It is a state like quantum state. Any other state, it is a state where the universe was in plasma. Right.
Yes. I don't know. I have thought of better names for it myself, but I have never come up with a better name. Just the expanding universe doesn't work because, as you know, Hoyle-Narlikal theory was also expanding, but it was different. It didn't have a hot Big Bang phase in the past. So today we use, as scientists, we use the name Standard Model of Cosmology. It's a boring name, but it's probably better than Big Bang. So.
Right. So, Nitish, you got your answer. Why it is from Big Bang and not from anything else. We go back to the part. So, shall I go to the next part, sir?
One last comment here.
Yep.
For inflation to explain the observed properties of the universe, especially to explain that temperature of CMB is same all across the sky, universe needs to expand by e to the power 60 times within a fraction of a second. So this is really a very violent accelerated expansion. That's why it's called inflation. Okay. So universe expanded by at least e to the power 60 times within a fraction of a second. And then somehow this energy all went away. So let's go to the next slide.
Yes, and thank you, sir. Yeah, I will go to the next slide.
Okay, so how do you get acceleration? This is just a detailed slide about explaining how do you get acceleration in general relativity.
This is my favorite equation, which I've been working and explaining for years.
Yes. So that's why I had a sort of simple explanation without equations for those who do not like to see equations. For those who would like to see some equations, I have this slide. So the Einstein's field equations, which explains how gravity works, is there in the box in the top. The left-hand side is basically telling you about the curvature of space-time, and the right-hand side is telling you what kind of matter and energy you have in the universe, their pressure, elasticity, everything about them. Okay. Now, if you apply these equations to a homogeneous and isotropic space-time, a homogeneous and isotropic space-time is explained by one quantity, which is called scale factor A. Okay, and the scale factor A, which basically distance between two faraway objects, how it's changing as a function of time. The time component of Einstein's equation gives you the Hubble equation, which I probably showed you before. It tells you how at what rate universe expands. Hubble square is really the summation of all densities in the universe. So you have matter, radiation, whatnot in the universe. Their total density really tells you at what rate universe should expand at a given time. Now, what happens to this expansion rate? Does it change or not? Whether it accelerates or decelerates? That's the second equation, which is space part of Einstein's field equations. That tells you that depends on a combination of rho plus 3 times pressure. So if you have a substance whose pressure is very negative, then rho plus 3p would be very, very negative. And there's another negative sign, as you can see there, and that makes scale factor positive, which means universe accelerates. Okay, so for universe to accelerate, you need a negative enough pressure substance, which I told you already without the equations. I want to pause here and want to explain why this is so. I'm not sure if you have ever seen anyone explaining you why a negative pressure means expansion would accelerate. Okay, so let me try and explain you from something that you would have studied in 11th or 12th class. Imagine you have a hot gas in a container. Okay, yeah, you have a hot gas and the container has a piston in it, frictionless. Okay, so you have a container, hot gas, and a piston. The hot gas, because of its temperature, it's constantly pushing the piston. So the piston is kind of moving. Okay, that's like the expansion of the universe. But a hot gas, when it expands, it cools down, right? So what happens is as time progresses, it cools down. So it pushes this piston slower and slower and slower rate. So the piston moves at a slower rate. This is basically like expansion of the universe slowing down when you have very positive pressure. Okay, so positive pressure is a substance which expands and cools down, which is what you would imagine in general in your day-to-day life, right? If you have a tire and you puncture and the air comes out, it's cooler. Okay. Negative pressure is a weird substance. Let me give you an example first. A stretched rubber sheet. A rubber sheet is lying on its own. You stretch it. What you did is you took some of your muscle energy and put it into the potential energy. So the rubber can do work. Now, if you leave it, it comes back. Okay. So by expanding it, you delivered energy into the system. You didn't take away energy. If you have such a system inside a box, what it will do is as the piston expands a bit, the system increased in volume and it has more energy. The system has more energy. So since the system has more energy, it expands the volume more and has even more energy, and it just goes on like a runaway process. Okay, so that's what expands the universe. And there is actually
I think this is the easiest, simplest, yet a very profound explanation of such a kind of a complicated part, which seems to be complicated. Thank you very much, sir, for making such a simple analogy.
Yes, and I want to say this analogy is actually exact. Not in all cases in general relativity, but in this particular case of homogeneous isotropic universe. In fact, the acceleration equation can be written as a law of thermodynamics, first law of thermodynamic equation. And in fact, you will see this in GR books also. Okay, so you can understand it like this. Great, so here is how you get repulsive energy by putting negative pressure. Okay, now let's go to the next slide. Okay, so what can source inflation? Inflation is a weird phase. You have to have this negative pressure. It has to be radioactive. It has to go away after some time. So how do you get? It turns out it's a very simple mechanism. You have a scalar field or scalar condensate in the universe. Okay, the scalar field is like it has some energy everywhere in space, everywhere. As a function of time, the field evolves and its energy also evolves. And its energy is a combination of kinetic energy, like at what rate the field is evolving, and it has a potential energy, which I have drawn here in this diagram. It turns out in Einstein's theory to have negative enough pressure so that you get acceleration. Twice of the kinetic energy has to be smaller than the potential energy of this scalar field. So that's a very simple condition. So if you have a flat enough potential and you put a scalar field, it will evolve very slowly. If it evolves slowly, then it pushes the universe and accelerates. So it acts like a repulsive gravity there. Okay. Now you may ask, why should initially the scalar field be moving slowly? Maybe, when universe was created, the scalar field was moving fast. Yes, but expansion of the universe quickly takes away all of its energy out of it. So if the scalar field was moving fast, expansion will dilute its velocity. This is what we call Hubble friction. So expansion is like a friction. It will quickly become slow one. Then it will accelerate the universe. So that will go for a while. But as the scalar field falls down its potential, as you can see in this diagram, eventually it will start moving faster and it will oscillate by the bottom. Then it is not moving slowly anymore. And then inflation will end. So here is how you obtain a radioactive acceleration or a transient acceleration in the universe.
So we got a question. Can I take it with your permission, please?
Absolutely, please.
Yeah. So there's a question from Physics C1D. Sir, are quaternions used in understanding cosmology?
They can be, I guess. I have not. Yeah, it's there may be. So I do not have a definite answer here. Maybe let's keep questions like this, which are interesting, of course, towards the end. Okay.
Fine. Yes.
Yeah. But thanks.
So shall I go to the next slide?
Please ask questions anytime. Yeah, I don't want to just keep speaking. I want to answer questions. Yes.
Shall I stick to this slide or go to the next one?
Let's go to the next slide.
Okay.
Okay, but inflation, it turns out, has two parts. One is the classical motion of this inflaton scalar field. It's called inflaton field, by the way. It's a name, like electron, inflaton. This inflaton field, classically, it's moving slowly, so it's accelerating the universe. But quantum mechanically, because of laws of quantum mechanics, Heisenberg Uncertainty principle, it is fluctuating. So it's creating this unavoidable quantum fluctuations all the time. And these fluctuations have importance for structure formation in the universe and our existence. So which is what I want to tell you next as a story. So if we go to the next slide. Yes. So it turns out you can study quantum mechanics or quantum physics during this inflationary process by using some of the techniques that you study in those of you who are in BSc and MSc. Some of the techniques that you already know.
We need to go to the next earlier slide once, because there's a question coming up from short comment. May I ask you why there is a question mark above reheating in the diagram for the inflation potential in the prior slide?
Very good. I'll answer that. Good question. It will come up in 2-3 slides from now.
Okay. Yeah. So requesting short comment to stay online. I will proceed with this, and sir will definitely answer to that. Please wait, because I understand as a professor, it is something which takes time. It comes sequentially. Yeah, sir,
yes,
please.
Yes, exactly. Yes. So you can use the techniques of quantum mechanics that you learn in BSc or MSc, for those of you who are already in BSc and MSc, to actually study what happens to these fluctuations during inflation. So I want to tell you that there's this famous physicist, Juan Maldacena, from the Institute for Advanced Study in Princeton, a very, very prominent physicist of this generation. He was giving a lecture and I was a student. I was there in this audience, in this photograph. And he told us a story. He wanted to teach about something else, but he decided to teach about inflation and quantum fluctuations. And he said that everyone should know about how quantum fluctuations work during inflation. Everyone, in the sense, every theoretical physicist. And he said it should be so important that when you are stopped at a costume and you say that, oh, I'm a poor person because I'm just a physicist. To prove that you're a physicist, you have to actually derive all the quantum fluctuations. Okay, so nevertheless, this is just a, it's of course an exaggeration, but okay. Now, the first time quantum fluctuations during inflation was kind of calculated was actually during a conference. It's a famous conference in physics. I hope, since most of you are physics students, you have
Sir,
heard
if I'm
many.
not wrong, and
Yeah.
Professor Daksh Lohia is featuring in this photograph, a former student of Stephen William Hawking.
Ah,
uh,
must be,
from
must be. Yeah,
from
yeah.
Delhi. Yeah, I had a very long discussion for 2 3 days about his experience because he was a direct student. He went to Cambridge,
Uh-huh.
met Stephen Hawking. I think the
Mhm.
person who is just standing right on the right hand side corner of Stephen Hawking is Professor Daksh Lohia.
I see, I
I
see.
had the
Glad to know.
opportunity, yeah, a long telephonic discussion. Then I used to make calls. He's in Delhi. It was during the COVID times. He came back and he talked about this, about his work on cosmology. He had got two students from Cambridge. And then we talked in Hindi because we came close to each other.
Right.
So just this wonderful picture actually reminded me. I got a little bit nostalgic. Sorry for interrupting.
Not at all. Very, very glad to know this. I didn't know this. So thanks a lot. I know half of these people here in this, know of half of the people in this photo. So always good to
Right,
know who the rest are.
right.
Okay, great. So this was a conference. It's one of those famous conferences in physics. You must have heard about the Shelter Island Conference, where Richard Feynman was presenting his Feynman diagrams and calculations. And then you may have heard about the Solvay Conference in 1925-26, where the quantum mechanics, this famous photo of everyone. So this is the inflation conference. It's called Nuffield Symposium. It was organized by Hawking and Gibbons and their collaborators. It happened in summer 1982. And amongst these are many great inflationary physicists who came up with this idea. There is Alexis Starowinsky, Andre Linde, Alan Guth, Paul Steinhardt, Michael Turner, Stephen Hawking, Jim Barden. There are many, many great physicists. Frank Wilczek. Frank Wilczek is a Nobel laureate. So they got together to compute what if I apply quantum mechanics during inflation, what do I obtain as an outcome? And I'm going to tell you about that. So if we go to the next slide.
Got another question if you if I
Yeah,
can take it.
yes,
Uh,
please.
Raghav is asking, sir, why the universe is continuously accelerating?
Good question. So for inflation, the answer is it did not. It accelerated only for a while when this inflation field was rolling down slowly. And after some time, the inflation field started to oscillate and then it stopped accelerating. So it was a transient acceleration. What about the present day acceleration, dark energy? Maybe in 10 minutes, we'll go to that. Okay. Yeah, I have to tell you the full story without taking too much time. So let me try to tell it in the next 5 minutes without taking too much
Sure,
time.
sure.
Okay. So all you do is basically apply Heisenberg uncertainty condition. You say that I have a scalar field. It has density and pressure, etc. But the density and pressure, etc., are fluctuating as per the laws of quantum mechanics. But Einstein equation says that curvature of space-time is related to what you put in the space-time. So if density and pressure, etc., are fluctuating, then curvature would also fluctuate. And these fluctuations would behave in a complicated way, which actually you can compute. So it turns out there are two kinds of fluctuations that you would generate in Einstein's theory of general relativity. The first is called a scalar type fluctuation, sometimes called curvature fluctuation. These names may be misleading. So these are standard names we use in cosmology. So this fluctuation is basically the temperature and density fluctuation in CMB that you see. So inflation creates these fluctuations. They're stored all through the history of the universe, which I'll show you how they're stored. And then at late times, these fluctuations start to activate the plasma, and the plasma starts to fluctuate, and that creates temperature. I'll show you how it happens.
Sir, one question I have from my end is that
Yeah.
whenever in cosmology, etc., we introduce the term or the concept of scalar. Now, is it that we want to make things easier because scalar fields are easy to map, etc.? I mean to say, is there any specific reason of putting scalar, the concept of scalar here.
Yes, yes. It's not to simplify in that way, but it's a good way to keep track of degrees of freedom. It turns out if you take a full tensor field, but since this is your question, Shaunak, I can answer a little technically. A tensor field can be written as a pure tensor part, which is transverse and traceless. Then a vector part, which is transverse, and a scalar part. So this decomposing a tensor into a pure tensor and vector and scalar helps us to study. So basically, you call one part pure tensor because their transformation properties are like a tensor and so on. So that helps us to identify and categorize fluctuations carefully. That's the only thing. And another interesting thing is if fluctuations are small, then the scalar fluctuation behaves on its own. It doesn't talk to the tensor fluctuations. The tensor fluctuations behave on their own. They do not talk to the scalar fluctuations. So they kind of decouple. And in technically, this is called SVT, scalar vector tensor decomposition theorem. It's only for small fluctuations. Okay.
I got it. Thank you. I'm going to the next slide, sir.
Yes. So inflation also creates tensor fluctuations. These are fluctuations in the metric. These are transverse and traceless. Technically, what it means is that if 2 points come closer, their orthogonal points go far away. And if they come closer, these go far away. This is called a quadripolar fluctuations. These will propagate as gravitational waves in the late universe. Okay. So here is, if I have to summarize non-technically, here is what it means. During inflation, the inflaton field is moving slowly. So it's a very friction-dominated motion. And the friction is really provided by Hubble, okay, in the sense because of expansion of the universe. That makes the universe expand in an accelerated way, almost exponentially. During this accelerated phase, the quantum mechanics forces you to have small fluctuations. You cannot ignore them. Heisenberg Uncertainty principle is a law of nature. So these small fluctuations, since the universe is expanding in an accelerated way, these small fluctuations are getting stretched. So they're created at very small length scales, but they're getting constantly stretched to very, very large length scales. If you stretch a small fluctuation to very large length scales in a very highly expanding universe, fast expanding universe, these fluctuations cannot flutter and average out. They will remain frozen as standing waves. So they become really like standing waves, these fluctuations. In this room right now, electromagnetic field is fluctuating because of quantum mechanics. But I don't see these fluctuations because, they're at very small scales on very shorter time scales. They average out on large length scales. I don't see them. But inflation doesn't allow that. It makes quantum mechanics appear on very large length scales, on the length scale of the sky. So basically, the accelerated expansion makes small scale quantum fluctuations appear in the sky. And they remain frozen in the sky all the way until very late times when universe eventually becomes a plasma phase. And then one by one, these fluctuations start to activate and start to flutter again. And that is the origin of all structure in the universe. Okay.
So Raghav Manchanda is telling that, Saurav sir, your way of explaining is fabulous.
Thank you. It's kind of you. Yeah.
Sir, shall I go to the next part, right?
Okay. Yes. Yeah. Shaunak, can I spend one more minute here before we move?
Sure. No
because
problem.
Because you know the time, so.
No. I don't have any time limit. As far as you're comfortable with your time, we don't have any problem.
Sure. Yeah. I also I'm also keeping track that I should not speak a lot because that should be boring. Because at the same time, I want to say enough so that later, if people watch this video, they can understand things better.
So a lot of people are they're listening, and you can speak, no problem.
Okay, so let's go to the next slide, and I want to show you a diagram, and I want all of you to pay attention. I want to explain this. This is one of the most beautiful things I have seen in cosmology, especially in early universe physics. Okay. First of all, let's look at this equation. I again explained you things without equation. Now let me explain with equation. This is a simple equation. This zeta that you see is, think of the parent field, which created all the density and temperature fluctuations in CMB, and hence all the galaxies and large scale structure today. Okay, so this is the parent field. We call it zeta. You can split this field. This is some random fluctuating field. You split it into a field with a long wavelength, then with a slightly shorter wavelength, then another shorter wavelength. This is basically Fourier transformation. Okay. So each wavelength would have a particular amplitude that is called zeta k. And it satisfies this particular equation, which all of you have seen in your even 11th class textbook. This is the equation of a damped harmonic oscillator. Okay. Here, n is log of scale factor. This is called number of e-folds, but you can think of it as time. No problem. It's basically like time. Okay. It's increasing as we go forward in time. So you have a damped harmonic oscillator, and there is a damping term or a friction term, which is d zeta by dn in red color that I have written up in the equation. What happens is that initially, when fluctuations are at small length scale, their wavelength is smaller or their frequency k is much larger. So the red color term in the equation is negligible. The blue color term is important. So you have d square zeta by dn square, which is like acceleration of this zeta field, is purely driven by the k square term. So these are basically oscillating. Okay, that's the simple harmonic oscillator. As time progresses, there is a k by ah factor, and a is the scale factor which is growing. Universe is expanding exponentially. So k by ah becomes very low. So you have a spring. Think of a spring which is oscillating, but the spring constant became negligible and zero. It will stop oscillating, and the friction remains almost constant. So because of friction, it will just remain frozen, and that's what happens to each and every fluctuation in the universe. So below in the diagram, I show you the green color part. Green color part is kind of like a apparent horizon. These fluctuations see like as if the horizon, the distance that they could catch up with, is kind of falling on them. So once they are outside the horizon, they become frozen. They will remain frozen for a long, long time. They will then inflation is over. Then this horizon starts to grow, and then these fluctuations will catch up, and then they will start to flutter again. And this fluttering is exactly similar to what you see in CMB. The exact pattern of Gaussian fluctuations, adiabatic fluctuations, fractal-like scale invariance is seen there. And let's go to the next slide. You can actually prove, which I'm not showing you here, that these fluctuations, the probability distribution of these fluctuations are Gaussian or bell curve. Okay, that's also very important. See, these figures that I'm showing here convey more than what I want to say here. So there may be more things written here, which you can ask me, I can answer. But
so the middle part is actually showing that typical fluctuation. It is a kind of a normal distribution curve in statistics and data what we do. Okay.
Exactly.
Okay.
And it says that zeta equal to 0 is maximum. That means that most part you would see universe is homogeneous and isotropic, right? There is no fluctuation, no zeta. But then small fluctuations have some probability. Large fluctuations have very low probability. So it's a very homogeneous universe.
Nature will always give us this kind of a normal distribution curve. This is again proven with this kind of a diagram.
It is, yeah, it is true only when you have central limit theorem applies. In this particular case, there was no guarantee. It's just one universe, and Gaussian in fact is a very special case. In general, it should have been highly non-Gaussian, some other distribution. The fact that it is Gaussian and not non-Gaussian tells us that it is quantum mechanics. And I want to explain. Right. I want to explain that for a second.
Sure.
If those of you who have taken quantum mechanics course, and if you have studied simple harmonic oscillator in quantum mechanics, you remember that the vacuum state or the ground state of a simple harmonic oscillator is Gaussian. The wave function is Gaussian. So the probability is Gaussian. Now in quantum field theory, quantum field is basically like many infinite number of simple harmonic oscillators. So if each oscillator is in ground state, the quantum field is in vacuum. And these are these vacuum fluctuations that we are studying. So the fact that we are seeing Gaussian means we are really seeing vacuum fluctuations in the sky. And that's very important thing. Okay. Okay, so...
Sir, we got a question from Fire Phoenix. He's asking, good evening, sir. My question is, will you be able to explain us the Gaussian curve in a bit elaborated way?
Great question and very relevant to this slide. So thanks, I'll definitely explain. What it is plotting is the probability distribution in the sense how likely it is to see a particular fluctuation. Okay, the fluctuation could be zero, which means that there is no fluctuation. So if fluctuation is zero, there is no fluctuation. That is the center part, and that has the highest probability. So the highest probability is to see no fluctuation, completely smooth universe, which is great, which is what our universe is. Then there is a slightly lower probability to have slightly larger fluctuation. Then if you go to slightly larger fluctuation, even lower probability, and so on. Positive side means, let's say, high density. Negative side means, let's say, low density. So universe would have higher density part, lower density part, and their probability will be low, low, low. That's the Gaussian bell curve, basically. And if the width of this curve is something sigma, then almost 99% of the fluctuations are within 3 sigma. Okay, and that's
This
what
is
we
basically
see.
the statistical part that you're
Exactly,
explaining.
exactly.
Yeah, thank you. Thank you
Yes,
very much. Yeah.
exactly. Yeah, yeah. Yeah, so let's summarize. What did we learn? We learned the following in the next slide. We learned that inflation creates these particular types of fluctuations. I want to stress that these predictions were made in 1980s. For example, I showed you the Nuffield conference, which is 1982. The first CMB fluctuation was measured in 1992 by Kobe. So these are not, inflation was not designed to explain observed fluctuations. Inflation was designed to explain the homogeneity of space. It gave you fluctuation as a byproduct because of quantum mechanics, and it predicted particular pattern. An exact same pattern was seen in the sky after many, many decades, again and again. So it was a prediction which came true, and that's the success. And in fact, we know the shape of inflaton potential roughly from the data. From the most modern data, it tells you that the shape of the potential should be like this, like a hill which is shallowing, plateauing a bit. Okay. I can spend more time here, but I would not like to. If there are questions, I can come back. It will become technical. So let's go to the next slide, which is very important slide. So here it is. Inflation can explain, in fact, inflation predicted this kind of particular pattern of fluctuations. This particular pattern of fluctuations, if you feed into the early universe, and then you look at the CMB fluctuation, here is a curve which is very important in cosmology. The y-axis tells you about some amplitude of temperature fluctuation in the CMB, and the x-axis is an angular scale. So basically you take a, go to the CMB sky and look in that direction and that direction, measure the temperature here and there. You would see 2.7254, 2.7256, something like that. So you know what is the fluctuation in temperature or difference in temperature. Do that everywhere in the sky. Okay, and then find what is the average fluctuation by squaring each of them. It's a technical point. Just take the variance and from there calculate standard deviation. As a function of angle, it will look like this curve that you see here. There is a red color part, which is the theoretical prediction that this initial conditions for the universe put by inflation, and there is dark matter and dark energy in the universe. That's all. And the blue dots are data. You see how many data points are there, and there is these features oscillating. They all fit amazingly. And all data points have error bar, and you cannot even see the error bar properly. So that means it's such a precise, this is a great success, okay? We predict something happened very long in the universe, and they've
So this
exactly
data
matched
is
it.
gathered, I mean to say, is it a computer generated image, or how we get
Actual,
this data?
this is an
Actual.
actual image. So there are these satellites, cosmic microwave background satellite, particularly this is from Planck's satellite. So this is an
Okay,
actual
okay,
image. Yeah,
okay. I got it. So Raghav Manchanda is asking, sir, in which field you are working? Sir, please explain your research.
I'll come
I
back to
think,
it.
yeah, yeah. I think Sir has got a very interesting paper, and we are going to talk about that by the end. So, Raghav, please stay there. I hope you're enjoying. Just a quick note that those who are joining late, we are in conversation with Dr. Swagat Saurav Mishra, and he has been fabulously explaining with minute details about accelerating universe. A lot of questions have come in. So if you're joining late, don't worry. You can later watch this podcast, which is still more interesting. And it is, we have a lot of promises, and we are going ahead with a very nice and a great knowledgeable speaker. So stay tuned. Sir, the next slide, please.
Yes, please. Yeah, yeah. This way. So wonderful. So inflation has been so popular, especially amongst people who do not work on inflation, that they just assume that inflation really happened in the past. Okay, if you see an astronomer giving a talk on cosmology, they would always start with universe started with inflation, and then this happened, that happened. Okay, I am not that sure. So if you go to the bottom of this page, I would not bet more than 80%, and I work on inflation. But it's so popular. I just want to say that in the physics community, it is so popular that many people just take it for granted that inflation happened in the past. I want to say that inflation has been successful in the sense, if you have 60 folds of expansion, accelerated expansion, it explains why universe should be flat and smooth and all that. But more importantly, it predicts exact pattern of temperature and density fluctuations in the universe by quantum mechanics. And this is the real celebration of success. Okay, it is so successful that if you go to the next slide.
Sir, we got one question. I'm sorry to interfere. I think you can. Fire Phoenix is telling, sir, kindly explain the quarks and leptons in terms of angular separation whenever you are ready.
I'm
I
not
think this,
sure.
yeah, this falls under the particle physics, a very technical question. I think that Fire Phoenix, you can later even look into Google, or if you want, I can help you to explain through some of my videos. We will do that. Right.
Sure,
Okay.
sure. Also, I'll
Go to.
request whoever asked the question to explain it a bit. What did you mean by angular? Maybe we can come back at the end.
Yes, yes. If you can explain what you mean by angular separation, sir can explain it. Yes, sir.
Great. So many of people who worked on inflation have received big awards in physics, Dirac Medal, and even fundamental physics prize, etc. I'm just listing some of them here. There are other people also. So it's a great success story. But now I want to come to in the sense, what is so what's big? So is it done? We understand everything about inflation. So let's go to the next slide, which is, do we know everything or are there open questions? Okay, there are many open questions. First of all, what is the origin of this field, inflaton field? What is this field exactly? I'm proposing as a toy model, but do I exactly know where this field comes from? I may not. Okay. And how does exactly inflation end? And how do you go from the end of inflation to the hot Big Bang phase where universe is radiation dominated? This period is called reheating because you're heating up the universe. Well, it should not be called reheating. It should be just called heating, but it's a historical name. And this reheating period, we do not know how it happened. This answers one of the questions that somebody asked, why there is a question mark in front of reheating in some of my diagrams. The question marks belong to those phases about inflation which we do not understand yet. So one is reheating, and this also answers one of the recent questions. What do I work on? One of the topics I work on is how does reheating happen? Okay, so I saw the quark question, by the way. I'll come back to it in a second.
So this question, sir, is answered. Why there is a question above reheating in the diagram? So, sir have now explained it, and we will come to the question that why is your what is the area of your research? This question by Raghav Manchanda. I will come to that. We will come to
I
that
think
part.
yes. The area would be kind of covered as we go along, but reheating is one area, for example.
Okay, okay.
Other thing is inflaton interactions. Was there inflaton field just by itself? Was it not interacting with other fields? Was it interacting with some vector field like electromagnetic field? Was it interacting with fermionic fields like quarks and leptons or some other fermionic field? Those create non-Gaussianity in the bell curve. The interaction of inflaton actually creates deviation from the bell curve because it's not happening in the vacuum in some sense. There's interacting, there's something else present. Okay. So that's an important part of inflationary physics. Then I also told you inflation creates tensor type fluctuations. These are called gravitational waves later on. And we have not detected gravitational waves from inflation. We are searching for it. So far, we have not. So that's why I said I will not bet more than 80%, but it's a very promising theory. It's most likely is correct. So, but there are
So
so
then,
many open problems.
what is the function of LIGO?
Yes, LIGO is one of the gravitational wave detectors. And inflationary gravitational waves do fall under LIGO band, but the amplitude that is needed So LIGO has a sensitivity in the sense the gravitational waves that are coming towards LIGO, they should have a minimum amplitude so that LIGO can pick them up. The ones that inflation create may or may not be that high.
Okay, right.
Okay.
May or may not be that high. Okay,
Yeah. Yeah.
got it. Okay, fine. I'm moving to the next slide, or will you
Yeah.
explain
Let's go to the
something?
next slide.
Okay, okay, yeah.
So there are many open topics in inflation. Next one. Okay. One is how inflation ends. I'm not going to talk now continuously. I'll just touch upon what they are. So each open problem, maybe 1 minute, not more than that. So exactly how inflaton field decays and how universe starts in a hot Big Bang phase. This is the origin of all matter in the universe. This reheating phase. So it's very important. And we do not know exactly how it happens. A lot of my research time goes into this. So this is one of the topics. If we skip many slides now, maybe 5, 6 more, we go to the next part basically. After that, there. Yes, that's about the tensor. Let's just stay on the name. Yeah, thank you. Now, that's about tensor fluctuations. Again, these are gravitational waves from inflation. I was telling you we're searching for it. We haven't seen it so far. And again, that's a topic which takes a lot of my research time. And I have slides here so that if somebody has a question, I can show. I am not going to go through them, but I want to show you one thing. If we go to
So
the next
I've got
slide.
a question.
Yes.
Sir, are you using primordial tensors for calculation of the angular momentum using Gaussian law?
So primordial tensors do have angular momentum. In general, they might average out depending on how you're producing in a coherent way or not. Gaussian law in the sense, are you saying that? Okay, I see. I think I understand. Do you mean that these tensor fluctuations are also created from a Gaussian distribution, just like the scalar fluctuations? The answer is yes. The tensor fluctuations are even more Gaussian than the scalar fluctuations. If the inflaton field interacts with other fields, then the scalar fluctuations or the temperature fluctuations may be slightly non-Gaussian, while the tensor fluctuations are predominantly Gaussian. So they are calculated using the Gaussian law.
Okay. We got another question. Raghav is asking, sir, what is gravitational wave astronomy?
Very nice. Let's go to the next slide then. This will answer that
Okay.
question. Yes. So gravitational waves are really the messengers of early universe. Why? Because gravity is a very weakly interacting force at low energies. The gravitational force between two electrons or an electron and a positron is many, many orders lower than the electromagnetic force. So gravity is a very faint force. Okay, it wins for planets and stars, etc., because they're overall they do not have charge, and overall they do not have strong and weak interaction. But compared to other interactions, it's weak. So the waves that are emitted from because of gravitational interaction are very difficult to emit. And once they're emitted, they're also very difficult to absorb. They just passes through most of the things. So very nice. So if they're created by early universe, let's say inflation, they will just come to you directly from inflation, which is the right-hand side diagram showing you here. While the left-hand side diagram is telling you if it's electromagnetic waves, it's coming from a star or a galaxy or an AGN, but it can come from the early thermal plasma of the universe, but not before that. Before that, universe was opaque, and light could not travel in a plasma because you cannot see the center of the sun. If you look at sun, you just see its surface. That's because the light that's coming from the center is getting scattered. Only the surface light is coming to you. Okay. So if you want to directly see the birth of the universe or earliest events, it's gravitational waves. Okay. So I hope that kind of answers. So gravitational wave astronomy is studying objects in astronomy, astrophysics, cosmology by using gravitational waves. So those objects which will emit large amplitude of gravitational waves, you can detect them. For example, colliding neutron stars or colliding black holes or a huge supernova or inflation in the early universe, etc., etc. Okay, now we skip all the equations and we just go towards one of the maybe the previous slide. I want to tell you the one before that. Fantastic. I want to tell you what is the wavelength of these gravitational waves coming from inflation. Okay, that really depends on inflation creates gravitational waves over 27 orders of magnitude. So their frequency can range from about higher than megahertz all the way up to 10 to the power minus 17, 18 hertz. Okay, so very high frequency to very low frequency gravitational waves. All of them are created by quantum mechanics during inflation. But I told you these quantum fluctuations are frozen for most part of the universe. So depending on their wavelength, they all start to become active at some point in the past of the universe. Those gravitational waves from inflation, which became active at the time of nucleosynthesis, when the first nuclei were formed in the universe, they would have a frequency 10 to the power minus 11 hertz, very low frequency. But those which became active in the quantum chromodynamics phase, they would have a nanohertz gravitational wave signal. And nanohertz gravitational waves can be actually detected by something called pulsar timing array. If there are questions later, I can explain. So this is something you can see. Similarly, those who came around the Higgs physics, electroweak physics, those would have a wavelength of about 10 to the power minus 5 hertz or so. And they can be detected by a future satellite called LISA, which will go to sky. Like LIGO is on Earth, LISA will go to sky. And even higher energy, gravitons can be detected, or gravitational waves from inflation can be detected by LIGO. Okay, so it really depends on at which frequency you have how much gravitational waves.
So we got one question, if you please allow. Short Comet is asking, will gravitational waves get weaker due to the expansion of the universe?
Yes, and exactly the same way electromagnetic waves get weaker. Okay, it's because the gravitational waves travel almost at the speed of light, so they're like radiation basically. So they will dilute as radiation, so that their amplitude will decay, very similar to those of electromagnetic waves. Okay, but there's a subtlety. I don't know if I should go here. What you measure about gravitational waves is the field amplitude, and what you measure about electromagnetic waves is the intensity, and that creates a bit of that's an advantage for gravitational waves. But let's not go there. I want to mention another thing which people ask me often is, do gravitational waves also experience gravitational lensing like light? If light coming near a black hole, it gets lensed, it bends. Does that happen to gravitational waves? Yes, absolutely. It will also happen to gravitational waves. It will also bend, and all of that would happen to gravitational waves.
So we got another question from Fire Phoenix. Sir, then can LISA deal with the mathematical inconsistencies in terms of quantum field theory?
Very good question. And yes, the answer is yes. Particularly, you see, LISA has a sensitivity, which is kind of like electroweak scale or Higgs scale. So and that's what Large Hadron Collider is kind of probing. If there is something new physics happening right around that scale, that right beyond Large Hadron Collider, something new happening, that is something, I won't call it inconsistencies in quantum field theory. It could be inconsistencies in standard model of particle physics. And those could be picked up by LISA. So that's one of the science goals of LISA.
Okay.
Very
Before
nice.
we go to the slide, one question, please, sir. Sir, can gravitational waves transfer their energy to electromagnetic waves?
Yes. Good. Gravitational waves, can they transfer their energy to electromagnetic waves? Gravitationally, yes. Gravitationally, they can transfer, but there is no special interaction between gravitational waves and photons. Okay, so they won't transfer energy by some direct process. They can transfer energy by gravitationally. Okay. Other thing is, gravitational waves are self-interacting. Gravity is a self-interacting theory. So gravitational waves can interact with themselves. That does not happen to photons. Electromagnetic theory is not self-interacting. So there are these subtle issues. But this self-interaction is important at very high energies. So at low energies, you can forget about it.
Thanks, sir. Thank you very much for addressing my queries. We go back to the slides, sir, now. This one is fine, or shall I go to the next one?
Let's go to the next one just to show them what kind of spectrum you get. So there are lots written here. Let's not focus on that. Let's just focus on the diagram here. And the maybe the previous slide. Yeah. The y-axis is telling you how much gravitational waves you get. And the x-axis is telling you frequency of these gravitational waves. Okay, so that's the plot. All the colored bands that you see, those are sensitivity of different detectors. On the left-hand side top, bluish color is Planck satellite or cosmic microwave background detector. Gravitational waves cause the cosmic microwave background light to become polarized in a particular way. So that could be detected by cosmic microwave background light polarization. Those are very low frequency or long wavelength gravitational waves. And then there is PTA written in purple color, that's pulsar timing array. Then there is LISA next to it in green color. Then there is Big Bang Observer maybe, or DESIGO, which is Japanese mission, which is not active yet, I guess. Sorry, I wasn't, Big Bang Observer is there, DESIGO is there. Then there is LIGO, you see, red color, advanced LIGO, and other things. Okay, those are the sensitivities. What inflation creates on very low frequency, we kind of know. We don't know its height, but we know the spectral shape, and that's this black color line on the left hand, towards the left hand side of this plot. Towards the right hand side, the gravitational waves may be higher in amplitude or lower in amplitude, depending on what was going on in the universe after inflation. Whether universe became radiation dominated, hot Big Bang, right after inflation, or it went through other phases that we do not know. That's the unknown history of the universe. And that can influence the way gravitational waves can come. So Shaunak was asking whether gravitational waves can come to LIGO. I'm not sure whether it was Shaunak's question or somebody else's. The question is, it cannot come to LIGO from inflation. Okay, if it comes to LIGO, it is too much gravitational waves in the universe, and if it is so much that it will produce too less amount of helium in the universe. So if you put a lot of gravitational waves in the universe would expand faster, and that will cause too less amount of helium than you see in the universe. So this is a bound, very interesting bound. Okay, so that was all about gravitational waves from inflation. Do people have questions on this part?
Yeah, no more questions, sir.
Great.
Can gravitational waves transfer their energy to electromagnetic? This has been answered, and the LISA part has also been answered.
Great.
So, shall we go to this part or the next
so
slide?
Take home message from here is gravitational waves are created by quantum mechanics during inflation. We have not seen them yet, but we may see them. When we see them, they will not only tell us about what was going on during inflation, they can also tell us about what was happening in the universe after inflation and before universe became hot Big Bang or radiation dominated phase. Okay, so that's an important thing.
So we got a question, rather a comment. Anji Krish is asking, so I see a huge frequency gap for the Planck region and all others. Hierarchy problem, is it?
It is a brilliant question. There is a huge gap. Here, the word Planck does not mean quantum gravity. The word Planck means Planck satellite, which is also named after Max Planck. So here Planck does not mean quantum gravity, so no hierarchy problem. But you have noticed correctly that there is a huge frequency gap between the Planck satellite, what CMB can see, and what nanograv detectors, pulsar timing array can see. In between, we haven't.
Shall I go back to the earlier this slide, which will be easier for you to explain?
Yeah, absolutely. That's the one. Yes.
Yeah, okay.
Rightly guessed. Yeah. Yes. So we have to think of some method in which, if the wavelength of gravitational waves are such that they're longer than what we are seeing in pulsar timing array, and they're shorter than what we can see in CMB. Is there a way we can build? Of course, we cannot build a detector which is as big as a galaxy or so we cannot. But maybe we can use some astrophysical objects to see. So far, there are no ideas. That's where there is a big gap there. And it has nothing to do with the hierarchy problem.
Okay. We got another question, rather two questions. First is that Phoenix is asking, sir, what can we change in the sensitivity of LIGO that can match up with LISA?
LIGO sensitivity can be improved by making better detectors. But when we say sensitivity improves, we do not change the frequency. We just change the fact that how small low intensity gravitational waves can be seen by LIGO. LIGO cannot, but its successors are Einstein Telescope and Cosmic Explorer, ET and CE in this diagram. Same
Event
frequency, but
horizon. Okay. Yeah. Okay.
ET is Einstein Telescope,
Einstein's
uh,
telescope. Okay.
and CE is Cosmic Explorer. They can see even low intensity gravitational waves. So that's how you improve it. And that's what we're trying to do in the next generation.
Okay.
LISA sees gravitational waves in a different frequency. So it's a different kind of detectors. They are not based on ground. They're based in the sky. And very good question, but there's a slight subtlety there.
Okay. Anji Krish is telling, okay, I got it. I mean to say why there
Yeah.
is a difference that he has got it. And there's a question from Physics 1 C1D. Sir, most of the time I hear people saying about fine tuning. Can you explain if this comes in today's podcast domain?
It does. We can change the topic and go to dark energy. Okay, let's come back to fine tuning in 5 minutes. Okay. So I just showed you one aspect of what you can do, what research work, open problems you can do. This is gravitational waves. I also showed you reheating, how inflation ends and how Big Bang starts. There are other things called primordial black holes, which I do not want to touch here. I will answer if there are questions, of course. So let's skip this part, because each of them could go for hour-long talks.
I think
And
you
yeah,
this would have been a kind of a huge course. The
yeah, yeah,
intensity of the PDF file I can see
yeah.
on my system. It's huge. So shall we go? Where shall we go? Okay, Steve.
Let's go
Sir.
further to. Mhm.
Yeah, yeah. But I have a kind request. If you
Yes,
can
please.
please explain this part because this is truly interesting, and I would love to know a little bit from you, please, if you don't mind. Hawking
Uh,
radiation,
Hawking radiation from a black hole.
right?
Yes. So black holes actually, classically in classical physics, maybe in the next page it'll show it nicely. The previous page, sorry, the previous one. That one, yes. Classically, if we have collapsing matter, so matter collapses, and at some point of time you form a trapped hypersurface, then you basically form a horizon, and this matter is lost. It's lost to whom? It's lost to an observer who is like far away. Okay, that's an observer which is far away. That observer would see that collapsing matter forms an horizon, and whatever collapsed, it's gone for them. And then the black hole will remain eternally there forever. The black hole can actually accrete other objects like we see in AGNs, etc. It will accrete matter and it can grow, but it cannot decay anymore. So it's a very fixed object, beautiful object, which is what Chandrasekhar's view of black hole, the classical black hole. Stephen Hawking found that the way quantum mechanics works, so around a black hole, it actually makes the black hole lose its mass by emitting radiation. And since this is a gravitational radiation, in the sense, I don't mean just gravitons. All radiations are created, but it's created in a gravitational process. And so this is very democratic. So it emits all sorts of particles. It emits electrons, quark jets, muons, gravitons, photons. Everything is emitted out of the black hole. And slowly the size of the black hole sort of shrinks, and the black hole can, if we think we have gotten the maths correct and the physics correct, then it seems like the black hole, nothing will stop the black hole. This is not because of quantum gravity. It's gravity and quantum fields. Just like in inflation, I had gravity, Einstein's gravity, and quantum fields on top. So Einstein's gravity and quantum fields, if I put, then the black hole is never going to stop. It will keep radiating. It radiates at a slow rate. So you may not see it for many billion years, depends on the size of the black hole. But eventually it will evaporate away. And towards the end of the process, it will emit higher and higher radiation. It will emit quarks, Higgs, everything, and it will just go in a final bang. This is a real bang. And if you see Hawking's paper, it's called exploding black holes or black hole explosions. So yeah, that's Hawking radiation. It has led to deep and profound issues in physics. I don't know whether we should touch upon that. I'm not an expert.
No,
Maybe.
sir, but one question I have, considering the legacy of Stephen Hawking, which I am also is a very big fan. You can I cannot turn on my laptop. I've got his photograph right on my desk. Now, there was a black hole information paradox with Gerard Hooft and Leonard Susskind was thinking that Stephen Hawking was telling that information should be lost because the black holes in due course of time would evaporate. And quantum physics tells that information cannot be lost. So there was a big problem, almost physics was collapsing. And finally, in that conference, I don't remember when they signed that bet, Stephen Hawking acknowledged, being a great soul, that his maths was wrong and information is not lost. It stays. Somehow, if you talk of the Hawking radiation, experimentally, it is a far away technique, which is obviously our technology doesn't support that we can see Hawking radiation from a black hole. So ultimately, what I am asking you, sir, hope you don't take me wrong, is that where do we stand? I mean to say, is it a great mathematical theory, or did he got his mathematics wrong and information is ultimately wrong, is not lost? So what is the conclusion? Where are we heading towards understanding Hawking radiation or Stephen Hawking's this contribution?
Sure. Okay, since you asked, let's discuss a little bit about it. Okay. Because it's one of the important problems in physics, in theoretical physics, in the past several decades. So let's talk a little bit. So early times, they sort of people after Hawking kind of pointed out that information is lost. Let me explain. Maybe this is not my topic of work, but I keep a keen interest in it. So let me explain what is information lost. It is often wrongly said that information lost means a black hole is formed, so whatever is inside the black hole, you cannot access it because you are far away. That's not information lost, because you can jump and eventually you will reach and you can see inside what it is. So that's not information loss. Information loss is the following. Black hole formed, and then it's Hawking radiated. You wait forever, and the full black hole has radiated and gone away. Okay. Imagine, suppose the black hole had formed from a material which is a pure quantum state. A pure quantum state has a high information. That's why I'm quoting it. So you know everything about it, and it collapsed. And then you waited. Hawking's calculations show that what comes out are thermal radiation. Okay, thermal radiation, pure thermal radiation. So what you see is a mixed quantum state. Okay. So what went in is a pure quantum state. What came out is a mixed quantum state. That only happens in an open system. In a closed system, always evolves as per Schrodinger equation. So if you start with the pure psi, you will get some another pure psi after late. You do not get a mixed state out of it. That is the puzzle. So,
okay, I got it.
So has it been solved? No, nobody knows where is it hiding the extra information. But I think what most physicists agree is the following, that the radiation that comes out is not purely thermal radiation. The radiation has some corrections. And these corrections this is a little easy to understand if you wait forever and the whole black hole is gone. That's probably, it's easy. So you're filled with radiation. This is not purely thermal. And in some way, the non-thermal part of this radiation is hiding all the information. What is complicated is, what if the black hole has lost half of its life? Has all the information come out in the radiation, or some of it is around the horizon or inside? Will it come out? This is the confusion, basically. And people are trying to exactly understand whether radiation comes out or not. So they have formed some alternate toy models of black holes. And in those models, they can show exactly that information is not lost. This happened in last decade, only in last decade. So the fact that Hawking signed means it's a change in his philosophical view that information is not lost, not that he could prove it is not lost.
Okay. I got it. Yeah. Okay. So right at this moment, this theory stands as it is.
Well, there's a lot of progress, but whether the final word has been said, I don't think it has been. I mean, it's not controversial. People would acknowledge.
Okay, so the problem is basically with the mixed state coming out of the black hole.
Yeah, so that's
not a pure state.
That's what we will say. The Schrodinger equation evolves things in unitary way. It's a unitary operator. It evolves, but it can never start with a pure state and give you a mixed state. In a completely closed system, there's nothing else that you have lost, etc.
Okay.
That's a simple way of stating.
Simple way of understanding, yeah. Firefelix related to this has got a question. It comes out as a mixed state, sir. Then is it because of the decoherence in the black hole?
That's one idea. That's one idea, that there is some decoherence going on. And this decoherence is probably more important when the black hole has not completely radiated. So some part of the black hole has radiated, and you see the radiation coming out. Somehow that is entangled with, with whatever is inside. Yeah, so that this is one hint which people approach the problem.
Quantum decoherence, I mean to say what you're trying. Yep.
Yes. Yes.
Okay. Another question coming up. Can't B modes be cause of scalar perturbations?
Okay. To give a bit of background to others, now we leave black holes and come to inflation. Inflation creates tensor fluctuations, which are gravitational waves. These gravitational waves pass all the way from the time of inflation through the cosmic microwave background plasma all the way to us today. And when they pass through the cosmic microwave background plasma, electrons which are moving in the plasma, they're moving in a sloshy environment which has gravitational waves. So basically quadrupolar perturbations. So sometimes the density in some part is getting squashed from here and expanded from the orthogonal direction and so on. That creates a particular type of polarization pattern in the photons that scatter from this electron and come to us. Okay, this is called Thomson scattering. So Thomson scattering from an electron, which was fluctuating in a quadrupolar way, would create a particular type of pattern. It's called B mode polarization. This is a telltale signature of gravitational waves, but this can also be caused by the cosmic microwave background light getting reflected on dust particles in our galaxy, like a frozen methane gas. And as a microwave photon comes and reflects and comes to us, this can also pick up some B mode contamination. So we call it foreground contamination, technical word. It means that. So yes, so primarily gravitational waves, but if you have a lot of dust in the galaxy, then they can overshadow.
So we come back to the topic because it is getting quite long. I think you will be also...
I think we should move on. So there are many problems in inflation, and we could talk all day and on many more podcasts, etc.
So
But
let me do, so shall I pause here? Outlook on early universe? Or
let's outlook on early universe. The next slide. Yes, so all I want take home message for everyone is that now we have an extended theory of standard model where universe did not begin in the hot Big Bang phase. It began, we don't know how it began, but there was an inflationary phase before the hot Big Bang phase. And from inflation, hot Big Bang was sort of created through the process of reheating, and then the rest of the universe walks through. That is our current picture of early universe that you should take home. So it's quite late. I think we can discuss a little about dark energy, but not more than 5 minutes, I think. I am happy to stay, but it's difficult for an audience, a person to listen to another person speaking for so long.
Not at all, not at all. Everybody is telling very nice, very nice. Good evening. So I mean to say, sir, I will tell you very honest, I'm very lucky. Considering other YouTube viewers, my viewers are very less, but they are absolutely on target. So I remember 3 hours long podcast going on with some professor. They're all live, all online. I'm so thankful to the audience that they are like that. And I am, I have really no word to thank you for this intensive and detailed podcast.
No, it's just it's a small thing for me to support your efforts. Yeah.
Thank you, sir. Shall I go to this part? This equation? Yeah. Okay.
If the audience, if the members in the audience are kind of okay with switching gear and talking about dark energy.
Yeah, I think it all follows in the sequence. So we are right on the track. Right.
Okay. So we know that we obtain acceleration of space if you have a negative enough substance, right? If you remember, I explained that if a substance has a lot of negative pressure, it creates acceleration.
Just to answer your question, whether the audience is ready. Thank you, sir. I'm a chemistry graduate, but I loved your talk. I'm very interested in quantum physics. We are ready, sir.
Yes, it's great. Very nice. Yeah. Let's not talk about dark energy too much, because we should spend some time on career, etc. if students have particular other type of questions. I am, of course, happy to come and give a full lecture on dark energy again. But okay, let's do a justice and give some overall picture of it. In this standard model of cosmology, a dark energy is supposed to be a cosmological constant, which means it's a component in the universe which has a constant density and it has a negative pressure, and its pressure is exactly minus of its density. Okay, so this is called a cosmological constant. And that, if universe has a cosmological constant, its density is always constant. While density of radiation is getting diluted, density of atoms, molecules, galaxies getting diluted, density of dark matter getting diluted. So at late times, universe is dominated by this constant energy or cosmological constant, and that can accelerate the universe at late times. And that's what we are seeing. We are seeing that universe is really accelerating today.
So this
Shaunak.
cosmological constant, you're talking of the cosmological constant in the Einstein field equation, which Einstein considered as a mistake, and later again, this now is being researched as a dark energy. That is the part.
Yeah, so good point. That point is the precise point of the next slide. So
Okay,
we'll come
fine.
to that point. Very
No
good
problem.
question. Yeah.
Yeah.
Yes. Okay. So universe becomes cosmological constant dominated at late times. If that's the case, then this first equation shows you that Hubble becomes a constant at late times. So towards the future, if we go of our universe, it expands at a constant rate. So it becomes exponential expansion, which is what you saw during inflation, by the way. Okay. And so you go into this exponentially expanding phase into the future, and universe will continue to accelerate forever at a constant rate. So you have a eternally accelerating universe into the future. This is different from inflation, where universe accelerated for a while, then inflation got over. That was a transient acceleration. This is an eternally accelerating universe. In such a
Sarangdas is
universe,
asking, are you talking about inflation, sir? I think yes, we are talking about inflation. The
now
whole
we are
topic
talking
of the
about
post. Dark
now we are
energy.
talking about dark energy.
Right.
Both are accelerating phases, but inflation happened in the very early universe and at a very rapid rate. While dark energy dominance is happening today, closer to present day, in the last 5-6 billion years. Okay, and so if dark energy is cosmological constant, we will go into an eternally accelerating space. It's a very, I want to tell you an anecdote here, a personal story. It is a very sad universe into the future, because universe will keep accelerating. So no new structure would form. Structure formation will be frozen. All that will happen is galaxies would evolve, stars will evolve, all stars would die, all galaxies would die, all black holes would eventually Hawking evaporate and go away. All the universe would be made up by some diffuse particles moving around, and most of the faraway galaxies will go outside your horizon. So a person living many trillion years into the future will not even see another galaxy. They would not even say universe is made up of several galaxies. They would just see Andromeda, Milky Way merging and becoming one, and they will not see faraway galaxies. So they would have a very different view of the universe, same universe, but very different view, okay? And nothing great would happen on very long time scale. Okay, this is very sad. And this is the first ever popular article I ever read in my life. I read it in 2008 on Time magazine, I think. It's called The Fate of the Universe. And I was very depressed, and that's the day I decided I want to do cosmology and understand dark energy. And I'm very fortunate that whatever I wanted to do, I could pursue, in the sense I'm doing research on dark energy. So it started from there, cosmological constant. Okay, with that story, let's answer Shaunak's question. What is cosmological constant? If we go to the next slide. Yeah, so some of these slides are made, first of all of these slides are not made for this podcast. They are just references, so I don't have to go through all of them, but they are made in a logical way. So many of the questions that you may have in your mind, maybe they're in the next slide, basically. The cosmological constant that I am calling dark energy is actually not just the cosmological constant that Einstein had introduced. This is what I will call a classical cosmological constant. It is a part of general relativity's equation, which is that green color lambda classical in this equation. Einstein had not included this term in his first ever paper. He included it later. It's again a great story. I don't know if we want to go, I can go, of course. And he then dropped it. But I think dropping it is not wise. Whether it should be dropped or not should be a matter of observational physics. Theoretically, this term should always be there. Okay, so that's the classical part. Then there is a quantum part, which comes from vacuum energy of all quantum fields. Quantum fluctuation creates vacuum energy, which behaves exactly like a cosmological constant. And what you observe, the observed density of dark energy, rho lambda, is a combination of the classical part that Einstein had in his equation and the quantum mechanical part, which comes from all quantum fields in the universe. It turns out the observed value is much, much smaller than what you would have roughly or typically expected from quantum fields. We have Large Hadron Collider operating. We know Higgs exists, top quarks exist, etc. They contribute to vacuum energy. And a typical value, nobody knows the exact value. A typical value would be like 10 to the power 70 times larger than what you have seen in the universe. So this is a fine-tuning puzzle, which we come to fine-tuning question somebody asked. If Einstein's cosmological constant in the equation of general relativity, you think of it as a constant of nature, cancels with the quantum field cosmological constant off to 70 decimal places, and then leaves the 71th decimal place, then you can explain dark energy. And this is an extreme fine-tuning problem. This is one example of fine-tuning in the universe.
Fine-tuning, yeah. Somebody was asking about fine-tuning, right?
Yes. There are many other fine-tunings in the universe. Again, that would be a very different podcast, but an exciting topic. What all quantities are fine-tuned in the universe and how they affect structure formation or existence of life, etc. Okay.
Sir, enthusiasm is at the top. Lot of questions. I don't know how to take all of them. First is that Waji is asking, sir, can we detect dark energy by any experimental means?
Good. Let's answer this question. Shaunak, I would need that slide because it's related to this question.
Okay.
So given that cosmological constant has fine-tuning, it has other problems, which if I can go to them. Each of these problems would be a full forecast, but it has other problems. And because of these problems, people have introduced dynamical dark energy which changes with time. Okay. One example is called quintessence. So if you go to the next slide, it will have quintessence. Maybe the next one. Yeah. The quintessence is just like in inflaton field. There is some scalar field in the universe, let's say, and the scalar field is rolling down slowly initially. So it is behaving like dark energy. And at late times, it can move faster and not behave like dark energy. Or the opposite. Initially, it was rolling down fast, so it was not behaving like dark energy. And at late time, it kind of moves slowly and it starts behaving like dark energy. So either of these cases would give you dark energy in the universe. This dark energy is changing as a function of time. So it's some kind of field, let's say inflaton field. Or in this case, it's called a quintessence field. And if you have a field, the field will have particles with it. So if there are means in which you can excite these particles in the lab, then you can see a dark matter particle. So other things that this field can do, if it's a scalar field and it is a very low energy field, it's becoming important or it's activating at very late in the universe, this field can carry force between other particles. Let me remind you of nuclear physics. The old theory of nuclear physics, the Yukawa theory, says that the strong force between a proton and a neutron, both of them are fermions, is carried by a meson, which is a scalar field, right? So scalar field can carry force between them. So if the scalar field has low mass, then long-range forces can be carried through them. These are called fifth forces. We have not seen long-range forces between these different objects. So there is some bound on the nature of these quintessence fields, but there's a possibility. So yeah, there is a possibility that you can test what dark energy is in the lab, but you have to be lucky because dark energy has to be that kind of dark energy which has an effect on lab. Cosmological constant has no effect on lab. It only acts on very long cosmological scales, so that you cannot test in lab. I hope that answers the question.
Thank you, sir. One question is that, okay, this is with permission from you. This is a very well-made presentation covering many topics. Will we get it? Well, Anji, I cannot send it to anybody without sir's permission. I think if sir allows, or you can write an email, which I will be putting in the description of this podcast, whatever about his discretion, he will do it. Thank you very much.
Yes.
Next question is...
All of these slides are, from my point of view, public property for all of you. So if we can find a way to put a link somewhere in the video later on, you can access
Right.
it.
Yeah. So do you have this uploaded somewhere? Any Google Doc or anything or so? No.
Yeah, let me upload it to on my website. I'll give all the
Okay.
link. We'll
All
now
the
go to the
links.
career thing, so I can show you the link
Career
there.
things.
You
Right.
can
So
click there and
Anji,
follow.
just keep an eye on my this podcast description. Once sir uploads and send it to me via email, I will upload it to this part. Another. Okay. Okay, sir, kindly explain fluctuations observed in the CMB radiation if you can. Will it
Okay,
take a
great.
long time? Yeah.
Yeah, I think let's finish dark energy. Maybe we can go back
Okay,
to
okay, yeah,
CMB
yeah, yeah.
next way.
Then what
Good
I will
question.
do is that, yeah, I have to keep this starred so that I remember this question. And also Raghav is constantly telling that the highly steady state theory, that is his part,
I'll
so
come
he
back to
will
it.
also
I'll
answer.
come back to it.
And sir, what does Hubble tension play here? Shall I mark it later or sir, will you answer right now?
Little later, maybe. Yeah,
A bit later. Okay.
yeah,
So we will go back to this part and I will go to the next slide, sir.
yeah,
This one.
yeah. So I don't want to talk more about dark energy too much. I just want to say that there is a new experiment on this slide, which actually is called DESI, Dark Energy Spectroscopic Instrument. It's in Arizona, and it has measured 14 million galaxies. It has measured their redshift and their distance, etc. And from there, we can know, since these galaxies are far away, we can know how universe has been expanding in between them, between the time when these galaxies emitted their light and it reached us. And that will tell us how dark energy is behaving in the universe, whether it's a cosmological constant or not. And to cut the story short, we go to 3 slides after this. And I'll tell you what they have
Three
found.
slides. 1, 2, and 3. This
Oh,
part?
sorry, one more. Sorry, yes.
Okay, yeah.
In the sense, 4 slides. One more, one ahead. Yeah. Slide number 94. Yes, sorry to confuse you, Shona. Yeah. So what this experiment is hinting at is, here is the diagram which I'm explaining you. On the x-axis is time progressing towards today. You can see today written there. So from about 10 billion years in the past all the way until today. And the y-axis, the colored, the sort of bright light, is the energy of dark energy, the energy density of dark energy. And what you see is, in the past, it seemed to have been growing a bit. And then it reached a peak about 5 billion years ago. And then it had started to decline by today. So it's behaving very, very weirdly. And it was growing in the past, it became maximum, and then started to decay. This is different from cosmological constant, which would have remained completely constant, or the quintessence field, which would have decayed, either initially constant and then started to decay, or initially decaying and then becomes constant. Either would have happened, but growing and then falling, we have never seen it. This is a weird behavior, especially growing. In an expanding universe, something is growing. Okay, it's such things are called phantom. So dark energy seems to be phantom, and there's a lot of research going on. And if I had come to dark energy an hour ago and I was talking about it, I would have shown you some latest research that we have conducted in this direction related to dark energy and extra dimensions of space, which can explain this kind of behavior. But I'm not sure, in the interest of time, how whether we should go there. We can come back to it, but I want to say that this is an important experiment. This is not a confirmed result. It's a hint. It's a strong hint, but it's not a 100% verified, confident result. In the next few years, more observations would come. And if they also show us this particular pattern of dark energy, then there is a huge paradigm shift that will happen in cosmology regarding what is dark energy. So dark energy is a mystery, but now we have experiments which can actually track down dark energy density over billions of years. So that can tell us what dark energy is. So let's be very hopeful. And this is a great field to do research on. If you are a student now and you want to become a researcher in dark energy, that's a great topic. Okay, so I could have explained it, but it might take time. I can come back to it if there are questions. If I go to some slides later, maybe 6, 7, slide number 99 or something, maybe a few more. There, okay. So I have talked about inflation and dark energy. As you saw, it's a vast topic. It's very difficult to talk about all aspects of inflation and dark energy within an hour or two. But I kind of touched upon few things so that you are aware of the kind of things happening in the research community. I also tried to sort of clear some misconceptions and told you some very exciting results, etc. But this is a broad field and it requires, there are lots of open questions which I have listed here on inflation, on reheating, on dark energy. And it requires physics, both standard physics like electromagnetism and statistics and thermodynamics and all of that. It also requires sometimes little exotic physics, quantum gravity, string theory, extra dimensions, and it's associated with gravitational waves and black holes. So it's an exciting topic in general. And yeah, and it is a topic which is constantly evolving as new observations are coming. Okay. And I list here all the topics that one needs to know, including, I should highlight that if you're an engineer and you build telescopes or satellites, you can also contribute hugely to this field because that's an important part. And if you are a computational physicist or a coding expert, you can do simulations and code and do data analysis, and that's also an important part. So, okay. Should we do the career thing and come back to questions if there is time, of course? No, these slides are just extra slides. I was showing what kind of the places that I have walked at as a scientist. One is Nottingham and the other one is in South Korea, in Daejeon. The kind of topics and groups that we work with in these two places. And you can see all those topics that I listed are actually being worked on in these places. And yes, so in this slide, right at the end, you see a website written. This is my personal website. I promise you that right after this podcast, I will put these slides on that website. I'll upload there. So if you go there, you'll find it. And I also provide a link to, if you want to understand theoretical physics in more detail, I've written some names here, Tassi and Lehousis, and ICTP, ICTS, David Tong's lecture, Leonard Susskind. You choose whichever you like and you can learn a lot. Okay, so that covers whatever I had to say. I can stay as long as you want.
A few questions coming up. I will just first of all take few questions. First of all, Raghav is asking that, sir, you have said at the end of the talk, you will explain your question, Narlikar steady state theory. So if you can just explain in short a little bit about this.
Yes, so the original steady state theory was by Hoyle, Bondi, and Gould in the 50s. I'll give you a little historical detail, which is slightly more than what people would usually say. So we had this Big Bang model, which is the expanding universe, which was hot and dense and expanding. This was pioneered by many people, mathematically by Friedman, Alexander Friedman in Russia, and later by Georges Lemaitre, both mathematically and observationally a little bit, in the mid to late 1920s. Then observationally by Edwin Hubble and collaborators. And then there were progress, but slow. And then notable progress was made by George Gamow in the 1940s and early 1950s. And he kind of proposed that the CMB light should be there and you should see it. And he also studied nucleosynthesis. So the Big Bang theory was in a good footing, but there were no clear observations which would verify that Big Bang theory is correct, apart from the fact that universe is expanding. That was clear. If you see galaxies, faraway galaxies, they are being redshifted. So light is getting tired and tired if you look at far away. So we knew universe was expanding. A puzzle came up in 1950s that there were objects discovered in the universe, stars, I think, whose age when you calculate from other techniques, came out to be larger than the age of the entire universe in the Big Bang theory that was studied at that time. So this became a puzzle. How can a star in the universe be older than the entire universe? Okay. And so that kind of prompted Hoyle and his collaborators to come up with a theory where universe is expanding, because you see that. But it was never in a hot and dense plasma state. It didn't have a beginning. It was expanding forever. It is existing forever. It doesn't change. As it expands, more matter is created in the empty space. It was a great and brilliant idea. And so there was sort of a scientific, healthy rivalry between people who thought Big Bang theory is correct and people who thought Hoyle-Narlikar theory is correct. Very soon, it was realized that the astronomers had made a mistake in calculating the age of those stars. So that thing went away. But other things came up. People thought of exciting observational tools to probe them. In 1965, cosmic microwave background was discovered as a thermal radiation coming from a thermal plasma state of the universe. That actually put an end to the steady state theory. But since then, steady state theory have been revived in different forms by Hoyle, by Narlikar, and other people. Steady state theory has very brilliant physics called action at a distance principle. This was pioneered by Richard Feynman in his PhD thesis. This is called Wheeler-Feynman absorber theory. They had done it for flat spacetime for electromagnetism, while Jan Narlikar and Fred Hoyle generalized it to curved spacetime. So it was good physics, observationally not verified. So we have to give it up, in my opinion.
Right. Thank you. Thank you very much, sir. Quick questions coming up, so I will be very precise and short. Sir, this is not some from this particular podcast, but one of my subscriber student asked that this person is basically got a MSc in physical chemistry as a major. Now, his question is that, sir, can you give me an idea about if he can do with the MSc in physical chemistry, a PhD topic related to quantum field theory and quantum electrodynamics? Is it possible?
Possible is always true. I mean, any scientist can change stream and become a scientist in a different topic and do PhD. So definitely possible. It may be difficult if your undergrad degree is in a different subject and your PhD is in a different subject. So it depends on country to country and state to state and the rules that are there. If
But
there
it
are
is
no rules,
possible.
I think it's possible. It is difficult. But if the rule says that you have to have a physics MSc, if the rule says, then it is difficult. You have to probably do a 1-year MSc in physics, then you can change 1 or 2 year MSc. If the rule doesn't say, then you can directly apply, but then it's up to the committee too.
Right. There are two similar questions coming up. From short comment, it is said that, is there any paper or books you would recommend to read and understand if one wants to go into research in inflation, any field of mathematics to understand?
Shaunak, can we bring up my slides and go to the references that I put for inflation?
Sure. I will do. Just a second. Just share my screen once. Just a second. I just stopped it, so I will just share it once more.
Please take your time. No problem. So while Shaunak is searching for it, any textbook on cosmology should be good. You should read the textbook that you like. Depend on at what stage. If you are an advanced BSc student and you want to learn cosmology, you can read, in general, if you want to learn cosmology, then there are many cosmology books which are kind of intended towards somebody who is in undergrad and want to do. There is Barbara Ryden, I think it's a good book for for somebody who is at slightly early stage and want to learn. There is also a book on inflation, I think. I'm not sure whether it's on inflation or introduction to cosmology, but there's by Andrew Liddell, and that's also a good book one can actually master. There is on inflation, there is a book by Alexander Vilenkin, a great scientist. I think it's called Cosmology for the Curious, if I'm not wrong. And that is a good book to learn. At an advanced stage, you can learn any textbook in cosmology. Generalrelativityandcosmology has a textbook, which is very nice. There is a textbook by Mukhanov. There is a new textbook by Daniel Baumann, which I personally like a lot because the notation, etc., are similar to the ones that I use. And then there are many. So all of these are good sources to read. And if you find any lecture notes to read, you can also read from there.
I will just share my screen. And
yeah, I think if you go to my website and go to links,
okay,
physics links, you will get it. Sorry.
Okay, your website, sir, can you just tell me?
I mean, in general, if anyone
Swagat,
goes to my website, to physics links, etc., I think many books are written there in different topics, and from electromagnetism, classical mechanics to quantum field theory and cosmology and stuff.
Okay, let me share it so that. Okay, I think I will provide the link to that because we have few more questions until the download is coming. Yeah. Okay. Next question is that, sir, can you recommend a few books which cover cosmology for +2 level, like for international astronomy and astrophysics for Olympiads, like explain cosmology topics with plus 11 and 12 physics topics? I think, sir, you just answered that they can visit the website and they can find it out.
Yeah, for 11, 12, I should apologize. I do not know anything offhand. I think Cosmology for the Curious by Alexander Vilenkin is definitely for 11, 12 class people. But I'll take this question seriously. I will investigate about it and I will list them on my website within a few days. Okay, good question.
Okay. Okay. The pending question is that what role does Hubble tension play here?
Hubble tension is a very important problem in cosmology. Hubble tension has to do with the following. You measure at what rate universe is expanding closer to today. Because as universe evolves for billions of years, the rate at which it expands changes over a period of time. So you want to know at what rate it is expanding today, and that you can know by two ways. One way is just measure at what rate it is expanding by seeing that distance to different objects closer to today. Okay, and this is called a direct measurement that you can do by, let's say, looking at exploding stars whose brightness intensity you know, and by seeing how dim they become as they come to you, you can know at what rate universe is expanding. There's a second way, which is that from the spot size of temperature fluctuations in the cosmic microwave background. There you assume that you know in the early universe what is the size of a particular temperature fluctuation spot, typically a hot spot, a cold spot, etc. And if the universe, you know the size of the spot, if universe has been expanding faster or slower in between this cosmic microwave background emission and today, then the spot will appear smaller or larger, right? So using that, you can also calculate Hubble expansion of the universe. And you assume you know everything about the universe, how much dark matter, dark energy, etc. Then what rate it is expanding. Both are very good experiments, very good observations. CMB is a much more precise observation in the sense it tells you what is the expansion rate within a small error bar. But both are good and they do not agree. One says it is 67.4 kilometer per second per megaparsec. Okay, it means that if you're one megaparsec away, if you're a galaxy, you are moving away by 67.4 kilometer per second speed. This is of course not real velocity. This is expansion speed. The other one says it is 73 point something. Okay, that something changes from year to year. So they're very close, but they don't match. And this mismatch has been established. So either there's something wrong about exploding stars that we do not understand, or about CMB that we do not understand, or the universe is not made up of what we think it is. It has some extra components, etc., which we have not taken into account. So it is very important to solve Hubble problem. It has been staring at us for many years now, more than 6 years. So,
Okay. One quick question. I think it will require a lot of time to explain, but if you can just touch base, what is quantum gravity?
so let's look at classical some field theory versus quantum field theory. Classical field theory simply means, think of classical mechanics. If I give an initial, at some initial time, a particle is here, at some final time it is there, what path it follows? You would say it follows that path which extremizes its action. It's called principle of least action. Other way to think is that path which Newton's law tells you to follow. Okay, so you know the path, that's called classical path. But quantum mechanics tells you it doesn't follow exactly that path. It follows all sorts of possible paths. Each path has a given amplitude. You add the amplitude of all paths and then take the square to find the final probability of final travel path. Okay, this is the standard quantum mechanics. This kind of way of thinking about quantum mechanics was developed by Richard Feynman, and it's now very important. The same can happen to a field. If you have a field at a given time everywhere in space, it is organized in some way. Let's say the temperature field in this room. And then after some time, the temperature evolves everywhere and it becomes a different configuration. How it goes from this configuration to that configuration, in classical physics, is a determined way. It's called classical field equation. But quantum mechanics said, no, it does all sorts of different things. For example, when an electron is scattering with another electron, so two electrons interact by Coulomb repulsion, and when the electron is scattering with another electron, what can happen is the electron can exchange a photon between them, or they can exchange photon that can become an electron-positron pair for a while, and that can become a photon, then become another electron-positron pair for a while, and all of that happens very quickly, and you just see the net effect. These are quantum fluctuations, and these fluctuations are important even in our day-to-day life, at least in the lab, for electromagnetism. Okay, for gravity, these fluctuations are very low. So gravity mostly follow what classical laws tells you, what Einstein's equations tell you. But if you go to extreme systems which have strong gravity at very high energies, especially if you're close to Planck scale. For example, if you have two particles and they're gravitationally getting attracted, what path they will follow if their energy is closer to Planck energy is not classical path, but there'll be quantum effects. And you can calculate the quantum effects the same way that you do in electromagnetism by using Feynman's techniques, and you are not going to get any sensible answer. You are going to get answers that blow up and give you infinities. So what you do, you can pump more energy into the system. If a lot of energy is put into a small system, it forms a black hole. And so you wanted to resolve and see what's going on. In the process, you create a black hole, and you want to resolve more, so you put more energy, but it becomes bigger black hole. So this is a very different thing from all other field theories we know of. So gravity seems to be a different beast altogether. And the quantum gravity is figuring out what is the quantum theory of gravity. It's not even clear the quantum field theory, the standard quantum field theory applies in this case.
Sir, one question from Symplectic Geometer, an interesting name. Are there awaiting mathematical challenges need to be solved for dark energy research? I mean to say, what he's asking is, are there any mathematical unsolved problems which, if solved, would lead to a better dark energy research?
So one problem which is mathematical but physics is solving the cosmological constant problem. Why the cosmological constant is small or even zero, we do not know. So that is something that we need to solve. Other thing is, what is dark energy? Let's say dark energy is some kind of field is coming from string theory, from extra dimensions or something else. We need to understand the maths of such a system. Let's say string theory is ultimately dictating how dark energy behaves. We should know the maths of such a theory very well. So those are kind of challenges that we have. Whether that involves mathematical problems, in general, in quantum field theory, when you have infinities, it involves mathematical problems. The way we kind of tame infinities in quantum field theory has very interesting relation with mathematics. One way we tame is called eta function regularization. that's related to Terence Tao's eta functions. So
It
such kind of
functions, yeah.
relations are also there. Yeah.
Sir, I won't take any question. First of all, let me thank you very much. And has been a very extensive and long. I think we have answered to almost more than 50 questions. Sir, the last part which you were telling is about the paper that you have written. And if you can talk, shall I download and you start talking? And in the meantime, shall I download the paper and you would like to show it? The
They're on the
desi blend
slides.
world.
They're on the slides, so we can show it from the slide.
Okay, just a second. Which part shall I go?
Towards the end of dark energy
Okay.
section. Yeah.
Oh, just a second. Problem is that it is taking a huge time to download. So that is the entire problem. However, questions and queries, Swagat Mishra, or Academy and Research.
Much before
Research
that.
Center. I don't think it is visible right now.
So maybe I can just say it without the slides.
Yeah, sure.
So what can cause dark energy? So this DESI experiment is kind of telling us that probably dark energy was growing, its density was growing in the past and now decaying now. How can you obtain it? It turns out you can, one clever way to obtain it is if you have an extra dimension of space, a large extra dimension which runs forever, an infinitely big extra dimension. So we have X, Y, Z axis. Let's say there's a W axis which runs forever. And gravity is free to move in all dimensions. So X, Y, Z, W for space dimension and time. Gravity propagates in all dimensions. But all fields like dark matter, electromagnetism, all other fields are fixed to our 3+1 dimensional universe. Okay. If that happens, the fact that gravity goes to the extra dimension, its effect is that gravity becomes a little weaker with time. Okay.
Is this the one you're talking, sir?
Sure, we can go to a diagram, maybe. Go to a diagram.
This one?
Yeah, we have shown this diagram, but
okay.
Sorry. Let's go to the next plot. Yeah, let's zoom in here on the left-hand side. Yeah.
This one?
Yeah, exactly. It's like that. So all material things are on this 3+1 dimensional space where we live. It's technically called a membrane or a brane, or we can just call it our universe. And gravity moves in the full hyperspace or bulk. Then since the fact that gravity is leaking a little bit, it's becoming weaker. Even a constant dark energy, which would have been constant in Einstein's theory, tends to grow in such a universe because gravity is weaker, so it's easier to accelerate. So it becomes dark energy density grows. But if dark energy is not constant, let's say this is a scalar field like inflaton field or a quintessence field which rolls down, then as the dark energy rolls, if it rolls faster than the rate at which gravity is weakening, then overall effect will be dark energy decays down. So if you have a dark energy which is initially constant and then decays, in standard Einstein's theory, it would have looked like a cosmological constant then decaying. But in this extra dimensional physics, it will look like a growing energy which is then decaying. And it turns out this nice idea actually fits the data very, very well. So it's an very interesting and exciting possibility if this DESI results hold up.
So this brane, sir, is something close to the brane of the string theory?
Membrane. So in here, there is no string theory. The reason it is the names are sort of inspired is because of the following. In string theory, all fermions, or all material particles, quarks and leptons, etc., are open strings.
Okay.
Open strings have a property that they latch on to a membrane. It's called Dirichlet brane. The Dirichlet comes from Dirichlet boundary condition.
Boundary conditions, yeah.
So then they're stuck on the brane, while graviton is a closed string. So that gravity can leak. So it comes from similar kind of ideas. These ideas were developed in 1990s, late 1990s by many scientists. And this particular kind of large extra dimension that I'm studying was developed by, again, many scientists, but the cosmological implications were studied by Varun Sahni and Yuri Stanov in early 2000s. So it's been there for a while, and observationally, we just found out that it's probably is very interesting for DESI results.
Shall I stop the screen sharing?
Sure. Yeah.
Okay. So thank you very much from my end. It has been a very extensive webinar, and I hope you enjoyed the questions also, sir, because there have been a lot of questions which have been asked.
Yes, absolutely. Yeah. Absolutely.
Okay. So thank you, sir. And I have no words to thank. It has been almost 2.5 hours, I think the second biggest podcast with a lot of questions coming up. Thank the subscribers and viewers. And I think sir has really enjoyed, because all the questions were very relevant, and every professor would love to answer questions rather than talking.
Yes.
So thanking to the subscribers also, we sign off from here. But sir, please stay online. I will just take 2 minutes after I sign off. I'll just have a word with you. Thank you very much. Please do subscribe to my channel, Physics for Students. And I am coming up with some new courses on Lagrangian and Hamiltonian mechanics and introducing quantum field theory for beginners. Thank you very much. And thank you, Swagat, sir. A wonderful podcast. Thank you very much. Just stay on the line.